Okay, so I was cut off at the tail end of the last video. I had basically finished this problem, but I just wanted to again talk about how, although we could solve this problem and did using the equation for loudness, loudness equals 10 times the log of I over I naught, using logs is it can be tricky. I'll admit. Um, Even I am a bit rusty on the algebra using logarithms. So a more common sense approach to this problem, as I was trying to illustrate at the tail end of the last slide, we had shown previously here that doubling intensity results in a loudness change of 3 decibels. So if we think about this problem here, we started with one trumpeter. If we think about just doubling one trumpeter, we end up with 2. And then if we double 2 trumpeters, that ends up with 4. So really, we could have done away with all of this logarithm mumbo jumbo and just simply looked at the fact that if we start with a loudness of 75 and we double the intensity, that will increase plus 3 to get to 78. And then we double the intensity again, another plus 3, and we end up with 81, which is the same answer we got by doing all that crazy algebra. So that perhaps is a better, more practical way to think about this. Every time you double the intensity of a sound, you increase its loudness by 3 decibels. Okay, here's another way we can think of sound waves. We want to calculate the displacement of air molecules for a sound frequency of 1000 hertz at the threshold of hearing. So that's something we haven't really talked about a lot. We mentioned it somewhat in the last chapter, chapter 11, when we were talking about waves. But the way that sound works is some vibration occurs. Like, I don't know, let's say we have a drum and we pound on it with a drumstick, and that vibrates the membrane of the drum. That then vibrates air molecules, which bump into other molecules and vibrate them, and then vibrate some over here. And what we end up with is a compression wave, where some of the air molecules get pushed closer together, and we have these areas of compression. Then we have these areas where they're spread out further apart, and then they're compressed again, and then they're farther apart, and then they're closer together again. So sound results from compression waves traveling through the air, which vibrates the molecules. So if we actually want to look at how these molecules move, how they vibrate, we can go back and look at some equations from the previous chapter. So first of all, the speed of sound, we're assuming this is room temperature air, 343 meters per second. What is the density of air? Well, we might have to go back to our chapter where we talked about density of materials and find on that chart the density of air and see that it's 1.29 kilograms per, this should be cubic meter if we're talking about density. And again, we've been using this as a constant for a couple problems so far. The I sub naught, the intensity of sound at the threshold of human hearing, 1 times 10 to the negative 12th. And then this is another, this is an equation from last chapter, chapter 11, when we were talking about waves in general. We said that the intensity of a wave is equal to 2 pi squared times rho, where rho is density, v is velocity, t is temperature, I think, or is it time? F is frequency and A is amplitude. If we want to know how much these molecules are vibrating, what their distance is, that's what we're trying to find, is amplitude. And so if we take this equation from chapter 11 and we solve it for amplitude, this is what we get. Amplitude is 1 over pi times the frequency times the square root of I over 2 rho V. Now, in the interest of full disclosure here, I did go back to chapter 11 here, verified this variable in this equation. It is time. And so by my calculation, if we solve this equation for A, there should be a time variable down here, which seems to just disappear. And I've been trying to figure out why that is, where that variable went to. Can't find it. Can't figure out why we are not considering time in this equation. So I'm assuming that we're just essentially assuming the time is 1 second. And because it's 1, it just kind of goes away. So basically what we're trying to do here is demonstrate how small the amplitude of the air molecules are that we can perceive with our human hearing. I debated on whether or not to just completely eliminate this example problem from the presentation, since I can't quite figure out where did the T go. But I'll go ahead and leave it in, and just basically so we can get to the final answer to see how little air molecules need to move in order for us to hear them. So there's my vibrating air molecules. And so plugging in what we know into our equation, that equation again is amplitude equals 1 over pi times the frequency times the square root of the intensity divided by 2 rho V. We've got 1 over pi times our frequency was given to us in the problem statement as 1000 hertz times the square root of the intensity. We were told to find the amplitude at the threshold of human hearing. That's 1.0 times 10 to the negative 12th watts per meter squared over 2 times the density of air is 1.29 kilograms per cubic meter times the velocity of sound in air at room temperature, 343 meters per second. And so if we calculate all of that, we get an amplitude of just 1.1 times 10 to the negative 11th meter. And so that's an incredibly small amount. These air molecules do not have to vibrate much at all for us to be able to hear it. And that's really all that I needed to demonstrate with this example problem. The incredibly small amount that an air molecule needs to vibrate for us to be able to hear it. And there go my vibrating molecules again. So if we look at the human ear, basically the sound waves, they're going to come into the ear through the ear canal, and then they're going to hit the eardrum. And this is going to vibrate back and forth, which is going to cause a little bit of a chain reaction between these little bones. Again, this is not my area of expertise, but it vibrates the hammer, which hits the anvil, which vibrates the stirrup. And then we have these canals with fluid in them, and the vibration travels through the fluid to the cochlea, which then the auditory nerve, senses those vibrations in the fluid in the cochlea and takes that to the brain, which your brain then interprets as audible sound. So that's not really the main focus here of this, of course, being a physics class, but it is interesting nonetheless to consider the way that the physics relates to our biology and how these vibrating air molecules get formed into what we hear as sound in our brains. Another interesting thing about human hearing is the way that we are more sensitive to particular frequencies. So this chart is a little bit hard to read, but basically what we're saying is these at low frequencies, the threshold of human hearing, it has a fairly high sound level. So in other words, a low frequency sound has to be pretty loud for us to be able to hear it. It needs to be pretty intense. Whereas if we look here in this range, which I've highlighted yellow, the frequency here in this range, in this band highlighted yellow, it doesn't have to be very loud at all. It can be incredibly soft, and yet we can hear it. And so these various red lines here are indicating uh, various ranges from the threshold of human hearing all the way up to the point that will cause pain. So basically this area right here, which I've shaded yellow, I'll try to kind of shade it in here. I'm not great at drawing with my little bamboo tablet here, but basically it is showing us how within this range, within this frequency, we are more sensitive to these sounds. It doesn't take as much intensity for us to hear them as it would at a very high frequency. So at the high end, we would need to be at a pretty high intensity. At the low end, we need a very high intensity to be able to hear it. But in this mid-range, it doesn't take much intensity at all for us to actually hear it. And the reason why is this is the frequency of human speech. So it only makes sense that we would be more sensitive to the frequencies at which we speak. That makes it easier for us to communicate with each other. I think I'm going to stop here because that this introduces here, this slide, a new section, and we're going to be kind of changing up the topic. So it just makes sense to kind of end the previous video, and we'll start section 12.4 with the next one.